Really glad to be able to or to present the training to you all. Today is day 2 of the training, and we shall talk about a lot of interesting things pertaining to machine learning primers. Even before we get started, we should be aware of a lot of terms and terminologies. We'll first talk about those, and then we will get into the practical aspects of it. So let's give a try to understand math behind the scenes. We would not delve and get into extreme depth of math, but whatever is needed for us to understand the concepts of deep learning, we shall do that. So let me share the screen. So we would get into machine learning primer, and we would understand more about how to actually deal with the data and things of that kind, and then we will proceed further. Oh, am I not audible, friends? Are you not able to hear me? Please, can you confirm? Audible? Wonderful. Yeah. If a lot of people say that I'm audible, that means there is no issue at my end, right? So please fix your audio issues at your end. Thank you, and let's get started. So what is machine learning? And what is the difference between traditional programming versus machine learning? We'll first try to understand this aspect. When it comes to analyzing the data, first you will have the data which is raw data. From that data, you glean information. Meaningful information is what you would extract. From that information, you try to get some knowledge. And on that knowledge, you start taking decisions, which is wisdom. That aside, if traditional program is all about taking the data and then writing a program to get an output. So you have data, you write a program, you supply these to your computer, and your computer gives you the output. You have data, then you write a program, and then you get an output. If this is traditional programming, then what is machine learning? Machine learning slightly is going to act in a different manner, wherein you have the data, you also have the output. So when it comes to machine learning, what do you supply to your computer? You supply output and data. So the output variable and the inputs would be there, and you supply these to your computer. And the moment you supply these to your computer, what does your computer do? Your computer is going to learn the patterns between your inputs and your output. And then it would give you the program as an output. Program is something which is going to establish the correlation between output and inputs. Okay, it's going to establish a relationship, and it will give you some math equation. And when it comes to neural networks, you get an equation like this: plus W2x2 plus W3x3 plus W4x4. And all of these weights, including this B, all of these weights are learned by your computer, and your computer will spill out this as an output. So this is the difference between traditional programming and machine learning. In traditional programming, you have the data, you write a program to get an output. Whereas when it comes to machine learning, you have the data, you have the output, and then you get the program. There are different types of machine learning algorithms which exist. We have already yesterday discussed about supervised, unsupervised, and reinforcement learning. When it comes to supervised learning, the goal is to predict output given an input, one input or bunch of inputs. Given the inputs, you want to predict an output. And if your output variable is categorical in nature, categorical means, say you want to predict whether a person will default on the loan or not default. Would an employee resign or treat or not a treat? Would a person claim insurance or not claim insurance? Is a credit card transaction fraud or not fraud? All these are examples of categorical data. When you have categorical output, which you're trying to predict, then that business problem is called as classification problem. And when you want to predict a numeric output, for example, post this training, what will be the salaries of the various professors, right? Or what will be the salaries of students who might get a job? Just as an example, right? So here the output variable is numeric. Or what should be the loan amount which should be disbursed? What should be the loan interest rate, interest amount? So when you have your output variable, which is numeric in nature, then the business problem is called as regression problem. Okay. And you also have a specific problem where from a large pool of options, you give some preferences. For example, if you search on Google for some article from large pool of documents, it will pull the most relevant and show it to you. That is called as recommendation. Yes, Madhavi, absolutely. Categorical means true, false, pass, fail. Categorical can be either two or multiple classes. Okay, so your output variable can either be numeric or it can be categorical. If it is categorical, and if you have only two categories, then it's called as binary classification problem. If you have more than two categories, then it's called as multi-class classification problem. So you either have a binary classification problem or multi-class classification problem. Then we also have, okay, recommendation, sorry, let me take one step back. When you search on Amazon, or when you search on YouTube for a video, a few other videos would get recommended. Okay, that's recommendation problem. And then you have retrieval. Retrieval is actually Google search. When you search for a specific document out of a bunch of documents, it's going to retrieve the most relevant and give it to you. That's retrieval problem. We have also discussed yesterday in detail that when it comes to supervised learning, in your underlying data set, output variable is known. So predict whether a person will default on the loan or not, given the age, gender, income, so on and so forth. Hence, supervised learning is also called as predictive modeling. When it comes to unsupervised learning, output variable is unknown, or even if you have an output variable, you will mimic, or you probably try to imagine that output variable is unknown, right? Though you have output variable, you'll start treating that as one of the inputs if you want to apply supervised learning algorithms on that. And we also have reinforcement learning. Okay, these are a few things that one has to remember. Then a quick memory check for everyone. Let's see how many of y'all are going to get it right. There we go. If you have pathology images, and if you want to classify whether that pathology image is cancerous or not, then what kind of a problem is it? Is it classification problem? Or is it prediction problem? Or is it recommendation problem? Or is it retrieval problem? What kind of a problem is that? It's a classification problem, absolutely. It's a two-class classification problem, whether that image is cancerous or not. Okay, and then there is slight change out here. That's okay. Okay, so what will the stock value be tomorrow? I mean, what will be the stock market value tomorrow? If that's the problem that you're trying to solve, what kind of an issue is that? It's a regression problem, prediction or regression. Okay, so it's a regression problem. How much interest rate should I lend money to customer X for? How about this? It's going to be a prediction or regression problem. Absolutely. Is employee X about to retreat? Will an employee retreat or not retreat? Resign or not? What kind of a problem is this, friends? I request everyone to please respond on the chat window so that we have good interaction going on. Classification, absolutely. If you do video analytics, and if you want to figure out whether a person is shopping or stealing, then what kind of a problem would this be? It would be a classification problem once again. What objects are present in the image? For this, Classification, once again, you're classifying whether you have a man or a woman or an animal. It's a multi-class classification problem, absolutely. It's a multi-class classification problem. This shopping or stealing is two-class classification problem. Wonderful then. Good. Then what about the next one? How many MacBook Pro will I sell in New York in next year? The moment you have numeric values that you predict, it becomes a prediction problem or regression problem. Okay, if you extract the tweets from Twitter, or if you extract data from social media, or if you extract reviews about your product from Amazon or anywhere else, and then if you classify whether that tweet is positive or negative, then it becomes what problem? Two-class classification problem. Now, this would be an interesting question. Which song are you humming the tune of? This one. What would be your answer to that? Sorry, I forgot to, I think, share my screen. One second, huh? So sorry. Okay, sorry. Yep. What kind of a problem would this be? Which song are you humming the tune of? That means you forgot the name of the song, but you remember the tune of it. So you hum it. The moment you hum it, your system should recognize what song you are trying to hum, and then it has to give it to you. That's called as not prediction. It's called as retrieval problem. You're trying to retrieve, right? It's not reference, it's called as retrieve. Retrieval problem. Absolutely. Then how high the value of the land will go in the next decade? What problem is this? Yes, it's a regression problem or a prediction problem. Absolutely. Who will be the best match for you? There are a lot of websites for marriage, for dating, etc. What would your answer be for this? Who will be the best match for you? Recommendation, absolutely, bang on. It's a recommendation problem. So in this way, we have a lot of business problems. Next, let's get into deep learning. Let us understand history of deep learning, and let's understand a few of the applications. Post that, we'll get into some math part of it, because how much ever you dislike math, unfortunately, that is what is going to drive your entire machine learning. So history is as follows. A few years back, I would say before 2012, the algorithm which was actually dominating the world was SVM algorithm, support vector machine. And there was a stiff competition between two schools of thought. One school of thought, people were inclined towards SVM, support vector machine. Another bunch of folks were inclined towards neural network algorithms. And there was a stiff competition between these two. Because there was very stiff competition. And ultimately, the race is anybody's guess, right? Who won at the end? Neural network algorithms. But how did it become famous? There was a competition called as ImageNet competition. In this ImageNet dataset, for this particular competition, there were 1.4 million images given, and there were 1,000 classes. Okay, 1.4 million images and 1,000 classes. And people were expected to build a system such that, when an image is given to the computer or to this algorithm, it should automatically classify on what is the name of that image. And when people have extracted the features manually, manually when people have extracted the features from the image, what kind of features can you extract? If you have an image, for example, an image is made up of pixels. And the pixel intensity values range from 0 to 255. 0 means black, 255 means white. So from image, you can extract pixel intensity values. And these pixel intensity values are called as features. So when people have manually tried to extract the features, and when they then supplied that to algorithms such as SVM, support vector machine, then people achieved an accuracy of around 73% or so, 73, 74%. In the same year of the competition, when people tried convolutional neural network, a variant of neural network algorithm, they achieved an accuracy of close to 84%, 84, 85%. That was a significant improvement, approximately 10% improvement. And that is when the entire world was like, oh, what's going on? So until then, in this competition and also otherwise during the research, when people try to work for an entire 1 year, when they try to do research for an entire 1 year, the percentage improvement in the accuracy was around 1%, 2%, that's it. And suddenly in this year 2012, they have seen a sudden improvement of 10%. The world was like, okay, what is this algorithm? Let's have a look at this. Seems like it's giving amazing accuracy. And from that year on, every year, the competition, ImageNet competitions were won only by those teams who have used neural network algorithms. And hence, 2012 marks the, sea change in the way people were saying neural network algorithms. And who actually built this in 2012? There was a guy by name Alex Krzyzewski. He was a key guy, and there were 2 other people along with him. They have actually come up with neural network, and they built this, and they won the first place. That was a revolution which happened. And that neural network algorithm is named as AlexNet. And since they're on, any team that has competed started using neural networks only. This is a history of thing. Alex Krzyzewski and his team actually have worked on that. what does this architecture mean? What insight should we draw? We'll get into that. Step by step, we'll discuss. So there was approximately 10% improvement, and that was wonderful. Okay. And today, as we stand, when it comes to image recognition, the neural network algorithms are close to human performance. And that's the goal of artificial intelligence, right? What is the goal of AI? To automate human intelligence. So you have human intelligence, you have artificial intelligence. Artificially, if you can, equate human intelligence, automate human intelligence, that's artificial intelligence. And that's what happened. In the year 2015 itself, the AI application in terms of image recognition has achieved human performance. That's the amazing part. Then a few other applications are applications of deep learning and speech recognition, wherein you have Cortana, Microsoft Cortana. Okay, or you have Apple Siri, Amazon Alexa. All of these things are examples of deep learning, okay, in the space of speech. Then when it comes to the error rate has drastically reduced when people started using neural network algorithms. Atari Breakout, yesterday I've shown you that game. Then there is something called as AlphaGo. Lee Sedol is a champion of this game called AlphaGo. And Atari Breakout, which is a AI-driven application, has actually beaten the world champion, hands down. Okay. And in the chess game also, you try playing computer chess game. Defeating the computer game is extremely difficult, not possible for a normal person. And such a powerful world computer game called Stockfish was defeated by neural network algorithm called AlphaZero. Now, the image-related applications which are solved using deep learning have gone to such an extent that when you have an image, it will not just recognize what is there in the image, it will also give you a caption. That there are two pizzas sitting on top of a stove top oven. Then here, image captioning. Forget about just giving a name to this. It's literally giving the captions away, right? That there are a group of people shopping at an outdoor market. Then this is AI-driven chatbot, wherein you supply an image as an input, and it says that a man and woman are holding umbrellas. Then if you ask a question on what color is his umbrella, it will recognize that you're talking about this guy because you're using his. And it will look at what is the umbrella this guy is holding. It will recognize the color and then give you the reply saying that his umbrella is black. Now, when you say, what about hers? It should understand that her means you're talking about a woman, and it should recognize a woman in the first place. And then it should recognize that your previous question was related to umbrella. So here also you're asking what is the color of her umbrella. So it will go recognize her and recognize the umbrella, and it's going to give you a reply saying that hers is multicolored. And how many other people are there in the image? It says, I think 3, they are occluded. Occluded means one behind another. So if you see this guy is behind this guy and this woman. So it would be difficult to recognize this person, right? So that's what it means. And we have a speech generation models or text generation models. What Netflix, etc., they are doing is they are looking at all the super hit movies They're looking at what was the script pertaining to that. All these super hit movies, what was the script, movie script? And then when you supply it to your deep learning algorithm, your deep learning algorithm would automatically generate new movie script for you. And when you do a direction on that movie, chances are very high that it might become a success. That's the strength and that's the power of deep learning today as we stand. Deep colorization. You take your old marriage photos of your parents, etc. It'll be in black and white. If you just supply that to your deep learning algorithm, it would automatically do a color coding. It will automatically assign color to the images. It will look very natural. Look at this hen here. Look at how natural the color, deep colorization happens to be. And deep learning is everywhere, right? Be it cyber crime, be it autonomous or driverless vehicles, be it image classification, speech recognition, language translation, language processing, sentiment analysis, recommendation, life sciences, healthcare, media and entertainment, security and defense, you name it. Deep learning is in. Okay. And these are a few other applications of deep learning. You name it from, it's there. Deep learning is there everywhere today as we talk. Okay. Now that we have had a brief understanding of CRISP MLQ, which is a project management methodology, which has 6 phases. And we've already discussed about those 6 phases, just to once again show you. Here we go. These are the 6 phases. Business and data understanding is part of phase 1. Then you have phase 2, 3, 4, 5, and 6. We had a brief understanding of this. Then we have also run auto ML or auto EDA rather library to perform complete exploratory data analysis, which is part of your data preparation. And then today, when we started, we had a brief understanding of machine learning. What is when did deep learning actually kick off? And what are the various applications of deep learning? Yeah, so this is what we have discussed. Now, we will switch our gears to understand math foundation. Once this part is clear, once the math foundation is clear, we would then enter into the first algorithm in deep learning, which is called as perceptron algorithm. Then we will switch to multi-layered perceptron algorithm. Once we are done with multi-layered perceptron, we will get into convolution neural networks, wherein we'll deal with images. And from multi-layered perceptron onwards, you'll have theory and we will have practicals. When we use practicals, when we do practicals rather, I'm going to show you how to use your database, SQL database. How do you connect your data to Python? And how do you deploy your model in production? Predominantly we'll be resorting to Python Flask application. So we will throughout, when we get into hands-on, look at what is a database, how do you establish the connection with Python, And then how do we deploy the model in production? This would be a focus. So until we complete the math foundation and until we discuss about perceptron and deep learning primer, it'll be all theory, obviously. But this theory will help us understand these algorithms in a better manner. So let's get started with the math. Don't get bogged down. Okay, not needed. Slowly and steadily, we will understand all the details. So here we have mathematical foundations. Here is the agenda. We'll learn about optimization, derivatives. We'll not learn about linear algebra. Sorry, I should have removed that. That's fine. So let's understand. First of all, what is this optimization and why do you need it? If you're, for example, booking a cab, okay, and if you want to travel, then what would be your number one goal? You want to minimize the travel time. And even the driver who is transporting you will have the same objective. So the objective here is to minimize the travel time. If you're writing code, okay, then you'll have development team who will write the code, and you'll have a testing team who will test your code. Testing team wants to test as many lines of code as possible. So ideally, they want to maximize the code coverage. And when you have servers, you might want to minimize the downtime. Okay, when you have servers, for example, you have WhatsApp. You know, recently also WhatsApp was down. WhatsApp was down means you will not be able to send and receive messages. Why? Because the server behind the scenes was down. So your goal will be to minimize the downtime to a very great extent, right? And obviously, if you're into service industry, you want to maximize the user satisfaction. Then you have profit. Profit is equal to revenue minus expenses. This is a business equation. It's not a math equation, it's a business equation. Profit is equal to revenue minus expenses. The moment you have a business equation or a business problem, you need to convert that into a math equation. Okay. Mathematical equation. So converting the business equation into math equation is something which we have to perform as data scientists. So here you're saying profit is a function of revenue and expenses. These are two inputs, revenue, expenses. And your output will depend on these two. So you're writing in this way, y is equal to function of x1 comma x2. And this function is nothing but x1 minus x2. X1 is revenue, x2 is expenses, you subtract those two. Okay. And optimum value of the function is something that we want to identify. And we are now going to look at optimization, which is related to change, rate of change. Rate of change is called as derivative or this is also called as slope, or this is also called as gradient. Gradient or slope or derivative or change all mean the same. Okay, all mean the same. Now let's take an example. Suppose you have X and Y. X value is 1, 2, 3, 4, 5, etc. And your Y value, which is 1, 2, 3, 4, 5, etc. Okay. And say you have an equation like this. The way we have an equation, y is equal to x1 minus x2, which is derived from the business problem. On similar lines, say you got some equation from some business problem. F of x equal to 4x minus x squared. Here, when you say x equal to 2, when you substitute x equal to 2, what do you get? And you know for a fact that y is equal to f of x. So you can also write this as y is equal to 4x minus x squared. When you substitute x equal to 2 in this, you get 4 into 2 minus 2 squared, which is 8 minus 4, which is going to be 4. That means if x equal to 2, y is equal to 4. This value. When x is 2, y is equal to 4. Then when x equal to 3, that means you are changing the x value. Now the question that you need to ask is, if I change the x value, would the y value change? If yes, at what rate? That's called as rate of change. If I change the x value, by what rate will y value change? If you change the x value from 2 to 3, then what will happen to y value? Let's see. So here, when you say x equal to 3, it will become y is equal to 4 into 3 minus 3 squared, which will be 12 minus 9, which will be 3. So if x equal to 3, y is equal to 3. X is 3, y is 3. So you have 3, 3. So what's happening? Okay, y is decreasing. When you increase the x value, y is decreasing. So here, the rate of change or derivative or slope or gradient is negative. Okay, so when you change your x value, y value changes. All right, friends, so this is called as rate of change or derivative or slope or gradient all mean the same. Now we will build on top of this and try to understand more. Because when we get into deep learning neural networks, right, you'll have something called as gradient descent algorithm. The moment I say gradient, you should, the one thing that has to strike you is that I'm talking about rate of change. Descent means downward direction. Rate of change in the downward direction is gradient descent. Okay. So If you change the x value, how much is the change on y value is called as rate of change. In this particular visualization that you're seeing here, what do you think will be the slope, positive or negative? Slope or gradient, slope or derivative or gradient or rate of change, all mean the same. What do you think, friends? Absolutely, Uma, right? And I request everyone to respond, please. Yep, absolutely, Srikant. So when you change your x, and if a y value is increasing, that means the slope or derivative or gradient or rate of change would be positive. When you change x, if the slope is negative, then the derivative, gradient, or rate of change would be negative. Okay. One more very, very important thing that we need to remember is that when you have a single value, slope of that single value will always be zero. Okay, if you have a single value, slope of that will always be zero. Okay, just remember that, or undefined basically, because it's a single point. There's no change on x, there's no change on y. Slope is what? How much is the change on y for the change in x? If you're changing x value, how much is the change in y? That's called a slope. Okay. So here, you say y2 minus y1 divided by x2 minus x1. That's slope. Anyways, rest all is theory. Now let's get into a few basics of calculus. Derivatives. A few basics. The first rule here is the power rule. And here is the derivative. D by dx of x raised to the power n. When you have such an equation, when you find the derivative of that, you get n into x raised to the power n minus 1. Here is an example. F of x equal to x raised to the power 4. If I were to put it here, I mean, this can also be written as y is equal to x raised to the power 4. Why? Because y is equal to f of x. So instead of f of x, you can also write y. That's one thing. If you want to find the derivative, the way you write is d by dx of x raised to the power 4. This is one way. Or you can say f prime of x, or you can say y prime. Either represent in this way or this way or this way, doesn't matter. So here n is 4. So you write it as 4 into x raised to the power 4 minus 1, which is 3. You can write it this way. So either your derivative you represent in this way, or this way, or this way. It doesn't matter. Okay, it really doesn't matter. Four x cubed. Okay. What if I give you an equation y is equal to x raised to the power 8? What do you think will be the derivative of that? Can someone let me know, please? It's like d by dx of x raised to the power 8. What will the answer? Yeah, a lot of y'all are getting it right. Absolutely. Right? Isn't that simple? Yes, this is how we will learn. So n is 8. So you have 8 into x raised to the power 8 minus 1, which is 7. Now we have constant multiple rule. How does it work this way? So what if I say d by dx of 7 into x raised to the power 5? Anything which doesn't have an x would be treated as constant. So the 7 doesn't have an x, right, in it. 7 is a number. So it's a constant. You take it out. So it becomes 7 into d by dx of the remaining part, which is x raised to the power 5. So it becomes 7 into d by dx of x raised to the power 5 would be n is 5. So n is 5 into x raised to the power n minus 1, 5 minus 1, which is 4. So into 5 x raised to the power 4, which is nothing but 7 5s are 35. 35 x raised to the power 4. Okay, friends, this is how you calculate. 7, you take it out as a constant, and derivative of x raised to the power 5 would be 5 x raised to the power 4, which is 35 x raised to the power 4. Next, let's look at the summation rule. If I have an equation like this, summation, then you split that and you can write it as d by dx of x raised to the power 4 plus d by dx of 12x. Can you just solve this? And I'm going to give you quick 1 minute to solve this. I request everyone to please post on the chat window, friends. That's how we will learn. That's how I know that you are interactive. You're active in the class. So please feel free. I'll just give you a quick minute to solve this. Good. A lot of you all have responded. So this is like d by dx of x raised to the power n, which is n into x raised to the power n minus 1. So you write it as 4 into x raised to the power 4 minus 1 is 3 plus. This is like a constant. So you take 12 out into d by dx of, this is like x raised to the power 1. If this part, if you were to solve, it's like again x raised to the power n only, but n is 1. If n is 1, you get 1 into x raised to the power n minus 1. N is 1, so 1 minus 1 is 0. And x raised to the power 0 is 1. So 1 into 1 would give you 1. So 1 into 12 into 1 is 12. So you get 12. And that is exactly what a lot of you all have written. Good. Then we have a division rule. And I've already told you that derivative of a single number would be 0. So can you solve this and let me know what will be the answer, friends? A few of you all are lightning fast. Good. So I'll once again give quick 1 minute for people to answer this. And let me also tell that slope or derivative or gradient or rate of change all mean the same. Multiple times if we revisit terms, you will remember. Let's try to take this up. So here you can split this as d by dx of x raised to the power 4. We have a minus, so you put a minus. D by dx of 2x square plus d by dx of 2. Derivative of a constant is always going to be 0. And here, this is like x raised to the power n, which will be n into x raised to the power n minus 1, minus you have 2, which is a constant, into d by dx of x squared would be 2x. Again, same thing. D by dx of x squared would be like x raised to the power n. N into x raised to the power n minus 1. So you write it as 4x cubed minus 4x. Next, let us look at a real world problem and try to understand. While I was working for a Norwegian client, okay, I can explain this. For example, this, right? So it's an amazing place, and then very lively houses you find around the mountains over there. But the mountains are very old. So because of the natural rupture among the rocks, big rock might fall into the water. And you might feel that, so what? You know what? The impact of that would be no short of a tsunami. So a big piece of rock falling in this would mean it will engulf the entire region here. So the government officials there had an additional responsibility of ensuring that they evacuate the people faster, because usually people go for sightseeing, and if these kind of incidents happen, people will be scared. Same like Indonesia, right? Where frequently there will be there are earthquakes happening. Despite that, people are going to places such as Bali because there, I think the impact of earthquake is less, but nevertheless, still. Okay. So here, how is that related to this? Might be a question. Okay, let me tell you. If this is your water, and if a specific rock falls here, what would that create? That would create ripples. That would create ripples. Now, there'll be waves, right? Waves. And there'll be circular ripples. We want to figure out what is the speed at which the circular ripple is increasing. Thereby, you know that if there are huts or houses out here, within how much time would the ripples reach this? How much time do we have? And within how much time can people evacuate? Given this, the government officials will issue a notice saying that the houses that you're going to have should be far away from this center. Okay, so suppose the radius is given as 4t plus 3. And using some IoT sensors, if you can figure out that the radius, the moment a rock falls into the water, if you can immediately figure out on what is the radius of the first ripple, using IoT sensors, you can, they put floating IoT sensors, okay, on the surface of the water, and then they start tracking these things. So if the radius is 11, whatever, 11 centimeters or whatever, then if I substitute 11 in this, r equal to 11, and then when we solve this, you get t equal to 2. It's like r is 11, so 11 equal to 4t plus 3, which implies 4t is equal to 11 minus 3, 8, which implies 2 equal to 2. That's how we're getting this. And we know that area of a circle is pi r squared. So pi into, you have r here, r squared. So this is like a plus b whole square, right? A plus b whole square. So you write this as a squared plus 2ab plus b squared. If you do that, what do you get here? A squared, which is 16t squared, plus 2ab, 2 into 4t into 3 will be 24t, plus b square is 9. Then pi into this would give you this, pi into this would give you this, pi into this would give you this. And then when you add them up, basically you get like this. Okay, or not add them up, basically, when you take a derivative of this with respect to t, wherever you have t, it's fine. Wherever you don't have a t, that would be treated as a constant. What is the derivative of the constant going to be? 0. What will be the derivative of this be? 16 pi is a constant into d by dt of t squared. This would give you 2t. So 2t into 16 pi would actually give you 32 pi t. Then what will be the derivative of this? 24 pi is a constant into d by dt of t. It's like t raised to the power 1. X raised to the power n, right? N into x raised to the power n minus 1. So 1 into t raised to the power 1 minus 1 is going to be 0. That's 1. So you get ultimately 1. 1 into this would give you 24 pi. Okay. Now we also know that t equal to 2. So if you give t equal to 2 and substitute it, you get so much in this. When you say 2, 64 pi, 24 pi. So what do you finally conclude? That is more important. All those derivations, math, that's not important. What is important is, what do you mean by this? This means that if the radius is 11 centimeters, the area is increasing at the rate of 88 pi, which is nothing but 276.5 centimeters square per second. 276.5 centimeters square per second. Okay. That's the area. That's the rate at which it's increasing. Okay. So I just gave you this example so that you correlate to what we are studying. We also have something called as a product rule. When you multiply to u and v, you get u into dv by dx plus v into du by dx. Suppose you have these two, u and v. Suppose this is u and this is v. How do you write this as? You write this as u, which is x squared plus 3 into dv by dx, which is the derivative of that. Plus v into, which is 2x cubed plus 5x into d by dx of x squared plus 3. What do you think will be the answer? Again, I'll give you a quick 2 minutes to solve this. Please take 2 minutes and solve this, friends. Thank you. Yeah, friends. So what is the answer? Only a handful of y'all are responding. What about the other people? I request everyone to please kindly reply. Okay. All right. So here, how do you solve it? So it is x squared plus 3. And if you were to look at the derivation of this, which is d by dx of 2x cubed plus 5x, you write it as d by dx of 2x cubed plus d by dx of 5x. So 2 is constant, take it out, d by dx of x cubed plus 5 is a constant, take it out, into d by dx of x raised to the power 1. So this will be 2 into 3x squared plus 5 into derivative of this will be 1. So it's 6x squared plus 5. So x squared plus 3 into 6x squared plus 5 plus 2x cubed plus 5x into derivative of d by dx of x squared plus 3. Okay, x squared plus 3, which is d by dx of x squared plus d by dx of 3. This will be a constant 0. Derivative of this will be 2x into 2x, right? When you expand it and when you solve it, this is exactly what you get. That's it. Okay. If someone has already expanded, wonderful. Okay. Next, dy dx of u by v, which is called as a quotient rule. If you have u divided by v, then how do you write it? It's v into v is this x squared plus 3 into du by dx. When you find the derivative of that, you get this minus you have u, which is this, into dv by dx, derivative of that, divided by v square. So you square it. All the preliminary stuff is done. Okay. Now we need to get into derivatives and optimization. And there is a concept called as maxima. There is a concept called as minima. And we shall discuss this post our break. So we'll quickly take a break. And after this discussion, we'll get into the deep learning. And when we talk about deep learning, we'll talk about backpropagation algorithm, gradient descent, etc. Then everything will become easy because we now understand the derivatives to identify maxima and minima. Okay, so let's take a quick break, friends. What's the time now? I believe it's 3:17. So let us be back by 3:30 and we will take this discussion forward. Okay, I think we can get started. Let me see if there is any setting I can change. Okay. All right. So we have to now talk about derivatives. Okay, we are of course talking about derivatives in optimization, but we have to now get into maxima and minima. A quick recap. We have tried to understand crisp MLQ framework at a very high level, superficial level. We probably scratched the surface. And then we understood that there are 6 phases. And also we have briefly got introduced to Auto EDA. And we have also downloaded Python and Anaconda. And we have tried to look at Jupyter, Google Colab, and Spider. Those are IDEs, integrated development environments. Today, we looked at deep learning history and deep learning applications. And now we are talking about math foundations. Once we are done with math foundations, we will get into deep learning 101, if you were to call it in that way. Okay. And as part of this, we will talk about perceptron algorithm, multi-layered perceptron, which is also called as artificial neural network or dense network, etc. And here we will deal with structured data, columnar dataset or tabular data, which is structured. And when we deal with this structured dataset, you will have Excel file, rows and columns, etc. But then rather than take an Excel file, because that doesn't happen in the real world, we will pull the data from SQL database, one of the SQL databases, and we'll pull the data into Python, in which we will do data pre-processing. And we shall also do the model building and model evaluation. And once these things are done, we are going to deploy the model. And for deployment, we are going to use Python Flask. We'll use Flask application to deploy. So this is how we'll solve it end to end. While we solve it end to end, when we get into the theory, I would certainly talk about a few of the data pre-processing techniques. It actually makes sense to, learn why we implement. And also alongside, I'm going to talk about a few regularization techniques. Okay, so let me put it here. But what do you mean by regularization techniques, etc.? We'll get there. Slowly we'll get there, yeah. Okay, so let's understand this part. When you keep changing your X value, if your Y value increases up to a certain point, and then if it starts decreasing, then this point here would be called as a critical value. This is called as critical value, this point. Now questions, a few questions I have. If you have X and Y, and if you have a pink line like this versus a blue line like this, which of these two lines will have more slope or less slope? Which of these two lines will have less slope, friends? Pink line or blue line? Which of these will have less slope? Let me see. Let me look at your answers. I'll give you quick 30 seconds. I request everyone to reply. That is how I understand that you're interactive. Please, if I have two lines, pink and blue, which of these lines will have less slope? The blue line, right? Okay. Now yet another question. If I have a green line like this, now which of these three lines will have less slope? Pink or blue or green? Green. Absolutely, friends. Green line will have less slope. And what do you think will be the slope of this green line? What will be the slope? Zero. Absolutely. Right? No matter what change you do along x-axis, x value might be here or here or here, here. Whatever be the x value, how much ever you change the x value, y value will remain the same. It will not change. So the rate of change would be the same. So slope is equal to 0. Okay, so the slope would be equivalent to 0 actually. Okay, so just a moment, friends. So sorry. Okay, sorry about that. Okay. And if the slope of this line is going to be 0, what if I have another line like this? What do you think will be the slope of this line? Anyone? Slope will be infinity, friends. Infinity. So that means for a given x value, y value can be anything. The rate of change of y value can be anything absolutely. Right? So slope will be infinity for a line which is vertical. A line which is horizontal will have slope equal to 0. At this point, what do you think will be the slope? Slope of this line would be equivalent to slope of this line, 0, right? Slope of this line will be 0. What did I say? If any line is horizontal or parallel to your x-axis, it will be having slope equal to 0. So at this, for this line, which is slope equal to 0, if I equate the slope equal to 0, then I'll get the critical value. So critical value is that value where slope equal to 0 will have slope equal to 0. So for this, slope will be 0. Okay, fine. Point taken. If I have a line like this, if if I have a line like this, wherein as and how the X value changes, what will happen to your Y value? Y value will decrease. It will reach a minimum value. Then it will start increasing. So this point is also called as a critical value. And at this point also, slope equal to 0. Okay. So this is a point where slope equal to 0 once again. However, we know that when we equate slope equal to 0, you get a critical value. But here, this critical value is called as maxima, because it's a maximum point among all the possible points. And this point is called as minima, because this is a minimum point among all the possible points. But always, you might not have a single X. You might have multiple variables in your data set. In your data that you're using to solve your business problem, you might have multiple inputs. For example, if you want to predict whether a person will default on the loan or not default, there'll be a lot of inputs, right? Age, gender, income, education details. In that way, there might be multiple inputs. When you have multiple inputs or multiple features or multiple dimensions, you cannot visualize like this to figure out whether a critical value is maxima or minima. We cannot visualize, right? So what happens is, if you have one dimension, suppose the output variable, then fine, you can visualize like this. But what if you have two inputs? It appears like this. What if you have three inputs? Imagine another line going into your computer like that. We cannot visualize. If we cannot visualize, they will not come to know whether what is the critical value. Of course, when you equate the equation to 0, slope equal to 0 means you get the critical value. But is the critical value minima or maxima is something which is not known. You don't know that. Since you don't know that, there should be another way to figure out. Suppose you have an equation, y is equal to minus x squared. How do you find the critical value? Slope equal to 0. And we've also discussed that slope or derivative or gradient or rate of change all mean the same. If everything means the same, then take your equation, find the derivative of that, because derivative and slope mean the same. If you find the derivative of that, this is like x raised to the power n. D by dx of x raised to the power n, which will be n into x raised to the power n minus 1. So you get 2 into x raised to the power 2 minus 1. You equate it to 0. And when you solve it, you get x equal to 0, and that happens to be a critical value. You only know that it's a critical value. But how do you figure out whether this critical value is minima or maxima? Is this critical value minima value or maxima? How do you know that? We don't know at this point of time, right? So how do you do? We'll look at that. Say you have another equation. Find the derivative of that, equate it to 0. Why? When you equate it to 0, you get a critical value. 2x equal to 0 means x equal to 0. So this is a critical value, but we need to figure out whether this critical value is minima or maxima. Okay, we want to figure out whether this is minima or maxima. To figure out whether this is minima or maxima, what do we do? For this, there is something called as second derivative test. What do you mean by second derivative test? So we know that f of x equal to minus x squared was one of the equations. When you find the first derivative of that, f prime of x is minus 2x. That's what you do. And when you take this first derivative and try to find the derivative of this once again, it's called as second derivative. For the second derivative, you get minus 2. Okay, because x is like d by dx of x raised to the power 1. It will be 1 into x raised to the power 1 minus 1 is 0. 1 into 0 is 1. Okay. And we already figured out that critical value was x equal to 0. How? We found the first derivative. We equate it to 0. So minus 2x equal to 0, which implies x equal to 0. This happens to be a critical value. This happens to be a critical value. So you get this. If the second derivative, which is minus 2, the derivative of x is 1, so minus 2 into 1 is minus 2. This is less than 0. If the second derivative value is negative, okay, if second derivative value is negative, then critical value is maxima. This critical value that you got is called as maxima. If you get an equation, y is equal to x squared. When you find the first derivative, you get this 2x. And when you find the derivative of this yet again, you get the second derivative. If the second derivative value is greater than 0, you say that the critical value is minima. Negative critical value is maxima. Positive critical value is minima. Simple. That's it. That is exactly what we have done. We have taken the equation. You find the first derivative equated to 0. And when you solve it, you get critical value. How do you decide whether your critical value is minima or maxima? By doing a second derivative test. If the second derivative value is positive, then critical value is minima. If the second derivative test is negative, then the critical value is maxima. Okay. Now let's take this equation, and I request everyone to take quick 5 minutes. Okay. Now it's 3:50. I'll give you 5 minutes time. I request you all to solve this. Find first derivative, then equate to 0 to find critical value. Then take this first derivative and then find second derivative. And if it is negative value, critical value would be called as maxima. If you get a positive value, then critical value would be called as minima. Please solve it and let me know, friends. Yeah, you all are very fast, but then let's give our other friends fair bit of chance. Maybe 1 minute, sorry, 2 more minutes to solve. Okay, so let's see. What is the right answer going to be? Let's see that. Okay, so we first need to find the derivative. Okay, you first need to look at the first order derivative. So let me open my video as well and let's look into this. So if you find the first derivative of this, you get an equation like this, right? This is going to be your first derivative. Derivative of a constant is going to be 0. Derivative of this is 2x. Derivative of x is 1, so minus 3 into 1 is minus 3. So you get 2x equal to 3 and then x equal to 3 by 2. This happens to be a critical value. And we need to figure out whether this critical value is minima or maxima. The question is, how do you figure out? Okay. Using the second derivative test. So if you take this and find the second derivative, 2x minus 3, if you find the second derivative of this, 3 derivative is 0, then you have 2x. Derivative of x is 1. So 2 into 1 would be 2. So 2 is what you get, which is greater than 0. If you get a value greater than 0, then your critical value will be minima. Positive value if you get minima, negative value if you get that, it's maxima. Okay, next. This one would be interesting. Let's solve this. And I'll give you a quick, this time we should not take more time, 2 minutes. You'll have 2 critical values, mind you, because each time your curve need not be like this, maxima or minima. Sometimes your curve might be like this also. So you'll have a minima as well as maxima. This would give rise to an equation like a curve like this. So you'll have 2 critical values. That's the hint. So please find out and let me know. Let's see. I'll give you a minute or 2 minutes rather to solve this. I see that a lot of y'all are responding. Let's see. Okay, 1 more minute and we'll proceed further. I'll show you the solution as well. Okay, so now is the time for me to explain you the solution. Okay, I think I didn't disable and people started scribbling on the screen. Okay, so let's try to answer this. So when you find the first derivative of 2 would be 0, any constant. Here you get 3x squared, and here you get, for this you get 2x. So minus 3 into 2x would be minus 6. And when you solve it, you get 3x into x minus 2 equal to 0. And you have two critical values. When you say 3x equal to 0, x equal to 0, and when x minus 2 equal to 0, when you solve that, you get x equal to 2. Those are the two critical values. Then, when you take this, and when you find the second derivative, you get an equation like this. This will become 2x. 3 into 2x is 6x, minus x is 1, derivative of that, so minus 6. So when you take critical value 0 and substitute in this equation, you get minus 6, and minus 6 is less than 0. So if you get a negative value, this critical value will be maxima. That is what we have discussed. Then take the next critical value and when you substitute in this, 6 into 2 minus 6. So you get 12 minus 6, which is 6. It's greater than 0. When you get a number which is greater than 0, this critical value would be called as minima. This is how you calculate maxima and minima. Finally, a few very quick things. Scalar means just a single number. Sorry, friends. Sorry about that. Just a sneeze. Okay. Scalar means just a number. Vector is collection of numbers. And vector is represented by a bold alphabet or with a small alphabet raised to the power that line. It's like x bar, but a small x. If you take uppercase x and bar, that's mean. If you take lowercase x and a bar, that means it's a vector. Vector is collection of numbers. And then you have matrix. Matrix is a two-dimensional array. This is one-dimensional array. This is zero-dimensional array. Okay. So these are a few things that we need to learn. This is just from the motivation standpoint. I just put this. If something stands between you and your success, move it. Keep moving. Okay. So this marks the end of math foundations for us. What do we need to do next? We need to get into deep learning primer. Okay. And that is what we need to do. So just give me a moment while I try to pull out the presentation. And then I'm going to proceed further with deep learning primer. Before we get into deep learning primer, obviously, we need to talk about data mining supervised learning. Okay, we'll have to talk about that. And once I explain this, then we'll once again get back to the original discussion. So let me see whether everything is available. No. So just a moment while I try to get the appropriate document. Found it. Just a moment. I will have to get you the details. Okay, this guy has GIF images. I'm trying to get the GIF. Just one more minute. I'm just trying to pull up the most appropriate GIF image for you all. If I cannot find that, I would certainly resort to the video. I think I found the video, and this is what I'll have to depend upon. Okay. There we go. I'm getting this. Sorry, are you able to see the screen? Can you all please confirm? Everyone? Wonderful. So I am going to talk about this particular stuff, and then I'll periodically play it and explain further. So friends, I would here try to go for a spotlight. What's happening? It's probably not working, so that's okay. I'll resort to this. Okay. So whenever you work on projects, you would be given historical data. Okay. And the first step is for you to figure out whether the historical data is balanced or imbalanced. Say you have an output variable, which is whether a person will default or not default. So this is what you have, whether a person will default or not default. And then you have a bunch of inputs. So you have 10,000 observations. In total, you have data of 10,000 customers. If you look at your output variable, if you have 50% default, and if you have another 50% not default, then this is called as a balanced data set. If 40% are default and 60% are not default, meaning out of 10,000 observations, say 6,000 observations say that people won't default, and another 4,000 have default scenarios. Or if you have 30/70. Until here, it is called as balanced dataset. But if one of these two classes is less than 30%, say you have 29% and 71%, or anything around that, this would be called as imbalanced dataset. Okay, any one class. It might so happen that this is 80%, this is 20%, doesn't matter. If one of the classes is less than 30%, you say that your data are imbalanced. When you have imbalanced data set, and when you split the data as training and test, you have to apply any of these techniques. Undersampling, oversampling, smooth, modified smooth, ensemble techniques, so on and so forth. Okay, there are a lot of other techniques also which exist. Or you might have to randomly split the data. When you randomly split the data, you split this data into training and test randomly. Now you might say that, why can't I build my model on the complete data? Sure, you can. But what if your customer asks you, did you test it? When you go to your customer and say, hey, customer, I've achieved 90% accuracy. What would your customer say? Your customer will check with you on, how did you test it? Where did you test it? On which data did you test it? Right? Obviously, customer would ask that. So in order to give an answer to the customer, you need to have test data. Okay, so you split the data into training and test. Here you have your training data, here you have your test data. So 80% of your data is part of training. Another 20% of the data is part of test. So it is randomly chosen. So here from these 10,000 observations, observation number 2, 4, 6, 7, so on and so forth, randomly are chosen into your training data. If you count how many are there, you'll have 8,000 because 80% of 10,000 would be 8,000. And remaining 20% of observations would be part of test data. So whatever observations are not here, observation number 1, 3, 5, 8, so on and so forth, would be here. And if you count number of observations, 1, 2, 3, etc., you'll have 2,000. 20% of 10,000 is 2,000. So you have 2,000 observations in test. So you have your training data, you have your test data. Using the training data, you build your model. Okay, using your training data, you build a model. Building a model means your model is going to learn the patterns between Y and X, output and your inputs. Suppose age of a person is 32, gender is male, income is $10,000, graduation, the person has done graduation, education is graduation. Maybe people of this kind default. So your model is going to learn that pattern. And in future, if you have a person with 32 years, male, $10,000, graduate, your model will say that this person might default because in the history, people of this kind have defaulted. So that math equation and the pattern is learned. And the pattern is captured using an equation like this. And if it's deep learning, neural network, you'd have same equation, but instead of beta naught, you'll have B, W1 X1 plus W2 X2 plus W3 X3 plus W4 X4. In that way, You'll have the equation. And I've already told you that it's not just the random split. We have multiple other ways of splitting your data if your data are imbalanced. Okay, you have stratified sampling, you have systematic sampling, you have probabilistic sampling, non-probabilistic sampling, many other techniques. However, if your data are balanced, the best technique is randomly split. If you know that randomly splitting is the best technique, why do you need any other technique, right? Best, and all the other will fall here. So why do you want to go with anything else? But to answer, yes, we have probabilistic, non-probabilistic, and in probabilistic, you have random sampling, systematic sampling, stratified sampling, and many other sampling techniques. Okay. So once you get the model is a math equation which captures the patterns between your output variable and all of your input variables. Then what do? You take your model and now test your model on the test data. So you take each and every observation that you have in the data set. Okay, you take each and every observation that you have in your data set and supply it to your model. When you supply it to your model, you get the predicted value. Say your prediction says that person will not default for this first observation. But the actual value here say that also says that person will not default. Then you have a match. So that's correct prediction. Say you take the next observation, take all these inputs, supply to your model, and say your model says that person will default. That's a prediction. But your actual value here says that person might not default. That means you just got an incorrect prediction. In that way, for all these 2000 observations, for a few you might get correct, for a few you might get incorrect. Okay, for a few you might get correct predictions, for a few incorrect. And if you want to calculate the accuracy would be number of correct predictions divided by overall predictions. Number of times you have correct predictions divided by overall predictions. That would give you accuracy. So that accuracy, assume, is 20%. If the accuracy is 80%, then the error would be 20%. Okay. Not sure why this is not going away. Yes. So what you do is, if you're unhappy with this, if you're unhappy that the test accuracy is 80%, and if you want to achieve, say, 90% and above, what you now do is you go back and perform something called as hyperparameter tuning. For every machine learning algorithm, including your deep learning neural networks, you have hyperparameters. What are hyperparameters? Hyperparameters are options which can be tweaked. You can tweak or change the hyperparameters. So you'll change those hyperparameters and you'll again build your model on the same training data. Again, you'll get a math equation. You take that and again test it on the test data. This time, probably, you got an accuracy of 88%. If accuracy is 88%, sorry, error would be 12%. Say you're still unhappy because you wanted 90% and above. So what do? Once again, perform hyperparameter tuning. Once again, perform hyperparameter tuning. And once again, you build a model. Once again, you test the model on the test data. This time, say you got an accuracy of 92%. Accuracy of 92% means error would be 8%. But you know what? A few people call this as information leak. What do you mean by information leak? Yeah, you'll get the attendance in the next 5-6 minutes, and directly, I think, task Rajita would be collecting the attendance. Yeah. Okay. Back to our discussion. Why is it called as information leak? It's something like this, friends. A few people call this as information leak, by the way. If you take an exam, final exam, say you got less score, and someone gives you this information that you got 80%. With this information, if you're allowed to go back home, prepare well for the exam, come back and again take the test. This time, say you got 88%. Again, with this information, which is 88% accuracy, with this information, if you again go back and once again build a model and once again test on the test data, okay, if you keep doing this, that means your test scores are getting leaked. And because of that information leak, you're again going and preparing for the exam and coming back and taking the test. So this part is called as information leak. Okay, so this part is called as information leak, friends. A few people call this as information leak, by the way. When you have information leak, what do? We are going to now take this 80% data. If you observe here, this 80% data will now get split into 60% training and 20% validation. Validation data is also called as development data. And you have a lot of observations here, right? So you have 60% of the data here. And from this, you take 20% of data into this. Now what you do is you train your model on 60% of the data, that is 6,000 observations, and then test your model on 20% of the data, which is here. And then when you build your model and test it on the validation, you get validation accuracy. If validation accuracy is 80%, then error is 20%. Then again perform hyperparameter tuning. Again build your model. This time say you got an accuracy of 88%. Again you do that. This time say you got an accuracy of 92%. Now say you're happy. Once you're happy with this, then you go and test your model on the training data also. You need to test the model on training data as well. And when you test your model on the training data as well, Say you got a training accuracy of 93%. What does this mean? This means that training error is 7%. Now what you do is you compare, or once you figure out that, hey, this is the best model and my training accuracy is also high, validation accuracy also is high, then you go and test on your test data. And say you got some test accuracy of 80%, 90%, 92, whatever. That would be the final accuracy that you'll communicate to the customer. Alongside that, there are a few more things called as underfitting, overfitting, and right fit. What do you mean by underfit or bias? What do you mean by overfit or variance? Is something that we will talk about tomorrow, and we will take this discussion to the next level. I will stop here. And why did our team members share the attendance link? I'm not sure. Please, can you delete that, my dear friend? Whoever has posted that link from our team, please delete that message, because attendance will be captured by Rajita from task. Okay, please delete that attendance link. Whoever has posted from our team. Oh, okay. Then it's okay. Then it's okay. All right. Sorry, friends. So the attendance